All right, good morning, Steve. If you want to wait just a minute while I admit a few more attendees, then we can get started.
Just let me know when to roll.
Okay, Steve, let's go ahead and get started.
Okay, welcome all, and thank you for joining us for this 2021 Student Symposium Continuing Education Seminar titled Forensic Engineering Failure Analysis Case Studies. But before we get started, please let me share a few technical instructions with you. If you're having any technical problems, please visit Zoom support at support.zoom.us or type your question in the chat box. The recording of this seminar without permission from ASCE Texas section is strictly prohibited. All participants are muted throughout the duration of the seminar. If you have questions, please type them in the chat box in your control panel. Questions will be addressed at the end of the seminar. Now a quick message from 2021 Student Symposium Advocate Walter Partners.
I just need to check my screen share real quick to make sure I am sharing with sound. Give me a quick second here.
Hi, my name is Caitlin Schmidt. I'm a civil engineering student at Texas A&M University.
My name is Colton Smith. I am a student at Texas A&M University, class of 2018.
Hi, my name is Hannah, and I go to Texas A&M, and I'm studying civil engineering.
Walker Partners this summer, I spent 2 weeks in the field with the survey crew, and then I came into the office and did design on subdivisions and site plans.
I came to Walker Partners because of the people and how friendly everyone was and welcoming.
Working this summer, I gained skills that I can use in my future, such as using AutoCAD Civil 3D software and learning how to grade a site.
The biggest thing I learned from Walker Partners was watching a project go from design phase to the final report and everything in between.
I really enjoyed the field work that we got to do. I enjoyed getting to go out to construction management and inspection projects.
They treated me like I wasn't just an intern.
I would recommend working with Walker Partners to others because I just believe they're a stand-up company that tries to do what's right, and they are good at what they do.
The thing I've enjoyed most about working at Walker Partners is the people, definitely, but also the team feeling.
I feel that working for Walker Partners this summer, I was able to provide benefit by helping the engineers on whatever they needed, so I saved their valuable time, and then I also had a site project that I did most of the design on.
Felt like I could go to the Walker Partners staff with any questions I had. Everyone was very friendly.
Or probably the most important thing I learned this summer that was non-engineering related was just how to do good business and to really care about your product and your clients.
I'm so happy that I'm going to be an engineer, and Walker Partners has definitely set that in stone for me because of how much fun I've had this summer.
Okay, now I'm pleased to introduce our presenter, Bradley East, Director of Operations for Polaris Forensics Incorporated. Mr. East has a background in engineering and project management and specializes in the failure analysis of building materials and structural systems. He has an extensive experience evaluating damage from construction deficiencies, design errors, and structural collapse. Mr. East has a strong technical understanding of building codes and design and construction standards. Mr. East is a licensed professional engineer in Texas and 12 other states. He's actively involved with the American Society of Civil Engineers at both the local and national levels. He has served in various committees, committee chair and board member positions at the local level, and he is currently the ASCE Austin branch president. At the global level, Mr. East is a member of the Structural Wind Engineering Committee. I now bring you Bradley East.
All right, thank you, Steve. I hope everybody can hear me all right. Good morning. As Steve mentioned, my name is Bradley East. I am the Director of Operations for Polaris Forensics. And the presentation I have for you today is titled Forensic Engineering, failure analysis case studies. But before I get into this, let me just give you some real quick background information about who I am and who Polaris Forensics is. So I have an undergraduate degree in civil engineering from the University of Texas, Hook'em Horns. I like to say that I enjoyed school so much that I decided to stick around for my master's degree, which is also in civil engineering. My professional and educational background is kind of a mixed bag of both structural engineering and construction materials. I'm a licensed professional engineer here in Texas and in 12 other states. And as Steve mentioned, I'm also actively involved in the American Society of Civil Engineers, both at the local level and at the national level. So Polaris Forensics is a forensic engineering consulting firm. You know, to summarize it as succinctly as possible, we analyze and investigate failures. And we do a lot of claims investigation work for the insurance community. We do expert witness work for the legal community. And we also do a lot of due diligence and condition assessment work directly for owners and owner representatives such as developers. We are headquartered in the Dallas area and more specifically Plano. We have a couple other offices sprinkled throughout Texas. We are a relatively newer firm and we're very fast growing. We will be opening a Colorado office here in the next month, and we plan to open a Florida office here in the very near future. All right, so this is the course outline. I'm going to start out by giving you the definition of forensic engineering. I'll then go over some of the roles and responsibilities of a forensic engineer. And then I'm going to cover some terms that you may or may not be familiar with that are very much associated with forensic engineering and performing a forensic engineering investigation. And those are concept of failure, standard of care, failure hypothesis, and subrogation. And I'll highlight each of those terms with case studies. And at the end, I'll take any questions if you have any. All right, so forensic engineering is defined as the application of the engineering sciences to the investigation of failures or other performance problems. You know, in other words, we as forensic engineers apply the principles of the scientific method to solve a problem. And problems in our world are typically some sort of failure, and failures can run the full spectrum. You could have something on one hand that's is catastrophic as a structural collapse, or something on the other end of that spectrum that might be more of a loss of functionality of a material, or something that might even be considered cosmetic. All right, so functions and responsibilities of the forensic engineer. I've broken this down into 3 categories. Those being document review, data collection, and interviewing witnesses, and I'll cover each of those here in the next couple slides. All right, so document review, it's not the most glamorous thing in the world, but it does provide valuable information about the project and the loss. And some examples of some documents that we would review would be construction drawings, construction specifications, photographs taken by others, construction submittals such as change orders, requests for information, special instructions, you know, things like that. And, you know, being a forensic engineer, it would also be prudent of us to review other expert reports should they exist. All right, so what I want to mention here is that, you know, being provided with the necessary documents for review can sometimes be challenging. You know, for some projects, and this is especially true for projects involving fatalities, you know, not unlike the FIU pedestrian bridge collapse, which is what you see here on the slide, the sharing of information amongst the various parties that would be involved in a project sometimes gets put on lockdown. And a subpoena can overcome that, but the subpoena process can sometimes be very time consuming. So what I want to say here is that for some projects, and this is probably more applicable to public projects, you know, nowadays there's a lot of information that can be found online. Again, using the FIU pedestrian bridge collapse as an example, you know, we were able to track down all sorts of pertinent information just by doing a pretty simple Google search and becoming an online sleuth. We were able to find construction drawings, photographs, specifications, you know, and in addition to looking online, again, this is probably more applicable to public projects than anything else. You know, you can perform an open records request and track down information that way. So, you know, the point of this is that if it's proving difficult to track down information through traditional channels, there are other ways to find things. All right, so data collection consists of on-site work, off-site testing, and off-site research. Some examples of on-site activities would be photographic and video documentation, collecting measurements such as building dimensions, framing member sizes. You know, it's also not uncommon for some projects to use non-destructive testing techniques to collect data. You know, an example of that would be using ground penetrating radar to identify the reinforcing steel layout in a reinforced concrete member. For some projects, it's also not uncommon to collect material samples for testing at later dates. Again, an example of that would be obtaining concrete core samples for compressive strength testing or petrographic examination. You know, some examples of off-site research would be looking at weather data through various weather sources, looking at soil information through the USDA Web Soil Survey website, looking at historical aerial images, such as from Google Earth or pictometry or some other source. All right, so interviewing witnesses, you know, this isn't always allowed, and that's probably more true for legal projects than anything else. But if allowed, it is important to get a firsthand account of the loss. And this can, you know, not only provides valuable information, but it can also help piece together a timeline of events. And to share a story with you, so back many years ago, I was looking at a high-end residential house for hail damage. And when I'm doing hail investigations, a big part of what I'm trying to determine is what size hailstone fell at that particular site. And for this project, I had the opportunity to talk to the homeowner. I'm asking her just some real general background questions. And one of the questions I asked her is, was she home during the storm? And if she was, does she have any idea what size hailstone fell? And she excused herself, went inside her house, and came back out, and she had a Ziploc bag full of hailstone balls. And what had happened was that she was home, and after the storm had gone in her front yard and picked up these balls and put them in her freezer. And you know, half my investigation was over because I knew what size hail fell at that site, and I had that information because I had the luxury of being able to interview the homeowner. All right, so concept of failure is defined as an unacceptable difference between an actual condition or performance and the intended or reasonable anticipated condition or performance. You know, that's a mouthful. Things fail for many different reasons, and I'll walk you through some of the more common causes of failure. All right, so one of those being material defect. This is a good example that highlights that. So this is this is a clay tile roof, again, that I was asked to look at many years ago for hail damage. And you can see in this image here that, that there's all these little kind of surface spall marks on this clay tile. And, my initial impression was, yeah, this could possibly be hail related. But I was able to lift up this lap seam where the upslope tile laps down and over the immediate downslope tile. And that area is shielded, protected from overhead impact. And I was finding these same spall marks, which was basically the smoking gun that told me that this wasn't related to hail impact. And I'm not sure if you can see it in this image or not, but at each of these little spall marks, there's like a little white dot or speck. And it turns out that when they were manufacturing this clay tile material, it was manufactured inadvertently with limestone inclusions. And that limestone material over time absorbed water, it expanded, and it created these surface spall marks. This is a good example of what a material defect might look like. Overloading is another common cause of failure, and this almost always happens inadvertently. Nobody intends to overload anything. And a good example of this is I was recently asked by the City of Austin Fire Department to investigate a couple of their fire stations. So the fire department at two stations in particular had upgraded their ladder vehicles. And these ladder vehicles were considerably heavier than the vehicles that they replaced in their fleet. And the fire department kind of did things ass backwards. So they upgraded these vehicles. They were operating them in and out of these two fire stations, which had suspended reinforced concrete slabs. And it was like all of the sudden a light bulb went off one day, and they thought, well, because these trucks are so much heavier, maybe we'll involve an engineer to look at our floor system to make sure that it's capable of withstanding this additional weight. So that's kind of where we got brought in. And one of these fire stations was built in the 50s. I think the other one was built in the 70s. Of course, nobody had maintained any drawings or any construction documentation. So we basically had to go in and do a full as-built condition assessment from scratch. So we had to determine what the layout of these floor systems were. We had to determine what the framing member sizes were. We had to do a lot of GPR, non-destructive testing, to determine what the reinforcing steel layout was. We had to do destructive testing to determine what the reinforcing steel sizes were and what the cover depths were. And we had to take a bunch of concrete cores to determine what the concrete strength was. And so with all of that information, basically had to go back and reverse engineer and determine what the capacity of these floor systems were. And lo and behold, it turns out that with these new ladder trucks, they were pretty substantially overloaded. It turns out that luckily for the fire department, that this didn't result in any sort of catastrophic structural failure or collapse, but the floor systems were damaged as a result of this overloaded condition. There was certainly a lot of flexural cracking as a result of this. So this is a good example of what overloading might do. All right, so as you may or may not be aware, moisture can do all sorts of crazy things. This is a photograph that's taken in an underground parking garage. And this is an underground parking garage for a pretty high-end hotel facility in California. And what you don't see here in this image is that above this underground parking garage is this pretty massive outdoor recreational space. It's almost like a big courtyard. And in this courtyard, they had a swimming pool, a lot of nice landscaping. And it turns out that both the swimming pool and the sprinkler system for the landscaping were leaking, and water was just pouring into this underground parking garage like it was a sieve. And what happened is that over time, that water, and I should have mentioned, so this is a post-tensioned slab, and that water worked its way into the ducts of this post-tension system, and it corroded and basically failed the PT tendons. And these tendons were rupturing violently through the slab soffit, which is what you see here in this image. Fortunately, nobody was hurt, but a good example of what water is capable of. All right, so I'm gonna, in a little more detail, cover the FIU pedestrian bridge collapse. This is a good case study that highlights a design defect. Just as a caveat, there is a lot of active litigation that's ongoing as a result of this collapse and this failure. So I can't provide you any insider information, but I will tell you that there are multiple reports out there that have been issued by both NTSB and OSHA, and these are readily available online. And I will tell you that, based on my involvement in this project, the findings in those reports are very spot on. All right, so the image there on the top left is an image of the collapse after it occurred. Just to give you some background information here. So the FIU campus is located about 11 miles west of downtown Miami. So on the bottom right image, you've got the pedestrian bridge here. Directly south of it is the FIU campus. This roadway here, US Route 41, is a very heavily trafficked roadway. And directly north of that roadway is a residential neighborhood. And there's a lot of student housing over here. So the purpose of this bridge was to help with providing ease of access for students so that they could get to campus. This bridge was constructed using accelerated methods. And in this particular case, what that means is that it was actually constructed in this adjacent yard right next to the roadway. And they were able to do that and construct the bridge while keeping this roadway open so that they, basically minimize traffic disruption. And when that bridge was close to being completed, they moved it into position on the piers. And they did that in the middle of the night. They closed traffic to the road for not more than a few hours. They moved it into position, and then they put it on the piers, and then it was in its final resting position. And then when that was completed, they were able to open the traffic back up and then continue construction on this bridge while keeping the roadway open. So they put the bridge into position on March 10th, 2018. 5 days later, on March 15th, 2018, this bridge suffered catastrophic failure and it collapsed. And this occurred in the early afternoon on the 15th, and it collapsed on traffic that was traversing under the bridge at the time. There were a total of 6 fatalities, 5 of which were from, pedestrian traffic that had basically been crushed underneath the bridge. There were 2 workers on the bridge at the time of failure. One of the workers died, and the other worker was permanently disabled as a result of his injuries. So MCM was the general contractor on this project. I believe they have since altered their name to distance themselves from this project, but that they are still in operation. FIG was the design engineer And to my knowledge, they have gone bankrupt and are no longer in business as a result of this failure. All right, so it turns out that after this bridge was put into position, so this is before failure and collapse, it started to crack. And these images here show you some examples of what those cracks look like. And you can see that these are pretty substantial. I mean, these are certainly not hairline. That crack there on the right, you could easily stick your fingers into. And to kind of give you some reference on where these cracks are located. So this image on the left is a top-down bird's eye view looking at this node right here. So that's looking down on this node. And I will tell you that this is where the failure initiated. So this image here on the right is an elevation view looking at the bridge from the side, again, here at this node at the end of the bridge. So you know, when we were doing our document review on this, it was pretty interesting, some of the stuff we came across. And one of those being text message communications between workers. And this is a screenshot of that. So this just kind of gives you an example of how bad the cracking is. One of the workers sent this text message to another worker, and he described it as it cracked like hell. You know, of course, this was brought to the attention of the contractor and of the design engineer. You know, it is our understanding that FIG, the design engineer of record, you know, further evaluated this issue. You know, they purportedly did some additional analysis, looked at their design, and, you know, for whatever reason, they ultimately concluded that these cracks were not a safety issue. And because they deemed them not to be a safety issue, they didn't close traffic to that roadway, and they didn't install any sort of temporary shoring. Coincidentally, on the day of the failure, so March 15th, that morning, both MCM, the general contractor, FIG, the design engineer of record, and the Florida Department of Transportation were meeting on site to discuss this bridge and to discuss this cracking issue. And based on meeting minutes that we were able to get our hands on from that meeting, it turns out that meeting adjourned, I believe it was an hour or two before this bridge collapsed. All right, so I'm gonna just real quickly do my best to kind of explain what happened here. So this, again, is an elevation view looking at the end of the bridge. This is that node where failure initiated. So, you know, this web member here is a diagonal axial load carrying member, and it exerts a diagonal axial force on this node. And this horizontal member right here resists that force, which therefore creates an equal and opposite force across this connection or this horizontal plane. And that's what's known as shear. And that shear force is resisted by the aggregate interlock in the concrete. And it's also resisted by steel reinforcing bars that are embedded in the concrete. And it turns out that the shear capacity of that connection was incredibly under-designed. I mean, it didn't even come close to being able to withstand the loads that it should have been designed for. And you know, it's unfortunate that happened. That shouldn't happen. but because it did, this bridge failed, it collapsed, and people died. So it's this is a very tragic failure. Like I mentioned at the very beginning of this, that was a super quick, fast run through on this project. But if you're more interested in this, OSHA has reports out there, NTSB has reports out there. They're definitely worth looking at if this is something that piques your curiosity. All right, so standard of care is kind of also known as the duty of a professional, and it's defined as the level of care normally practiced by a reasonable and prudent professional under similar circumstances during the same time frame. So in other words, me as a design engineer, am I using applicable codes and standards that another prudent engineer would use to design some sort of structure or some sort of member? And I also want to mention that if this standard of care is not met, me as a design engineer can be found negligent. And I've got a good case study that kind of highlights this concept. So this is a resort on the East Coast. It's a pretty massive property. There's a big parking garage. There's an on-site casino, on-site hotel, and there's an on-site theater. And the theater had a vibration issue. And more specifically, the theater balcony had a vibration issue. And these are kind of just general photos of the theater balcony while it was under construction. This is a predominantly steel framed structure. So you've got these inclined steel rakers that are supported on pretty massive steel girders that are further supported on steel columns. And the seating for the balcony consisted of precast concrete panels. So it turns out that almost immediately after this balcony structure was erected, it became obvious that there was a vibration issue. And the attorney that we were working for on this project liked to joke that there were workers at the edge of the balcony, this thing was vibrating, they got sick and they threw up off the side, which didn't happen. It was a tongue-in-cheek comment, but the point he was trying to make is that this wasn't subtle. It was a very obvious vibration issue. And because they had this vibration issue, the original design team had to design a retrofit, which then had to be installed to alleviate this vibration issue, which it did. But, as is the case with projects like this, of course, this turned litigious. And the owner sued the original design team to basically pay for this delay in the project and the additional cost of installing this retrofit. The original designer maintained in their defense that because the structural integrity of the balcony wasn't compromised, which it wasn't, that the retrofit that had to be designed and installed was considered, quote unquote, a betterment to the structure. So we were asked to investigate this issue to for the most part, determine if there's a standard of care issue here. Should vibration serviceability been considered in the original design? So if you were to look at the structural notes on the construction drawings, it would refer you to IBC 2012 as the governing building code. And 2205, section 2205 of that code would refer the reader to AISC 360 for structural steel. And commentary section L5 of AISC 360 says, floor vibrations have become an important design consideration. And in addition to that, it refers the reader to this Design Guide 11 document. So in addition to AISC 360, both the Steel Construction Manual and ASCE 7, both of which are very well-known industry standards, also discuss vibration serviceability. And in addition to that, the Steel Construction Manual also references this Design Guide 11 document. So the image there on the left is the cover of the AISC Design Guide 11 document. You know, this is a fairly well-known standard with regards to vibration serviceability. It provides guidance and design consideration. And it also provides minimum tolerance limits for both sensitive equipment and human comfort. So I'm not going to bore you with the technicalities of vibration, but I will tell you that vibration is very dependent on the minimum fundamental natural frequency of the structure. And this table here gives those minimum frequencies for different activities in different structure types. And I will tell you that this theater balcony, this row here for lively concert or sporting events, is applicable to this theater structure. So we created a finite element model of this balcony using engineering software. We performed a dynamic response analysis, and based on that analysis determined, drum roll, that the fundamental natural frequency was 3.41 hertz. So if you go back to this table here, you can see that that is fairly substantially less than what it should be. Well, it turns out that, you know, in addition to our involvement, there were two other experts involved on this case, and that includes the design team's or the defense's own expert. And both of those other experts reached the exact same conclusion, that the fundamental natural frequency of this structure was less than what it should have been. So, you know, it turns out that this is definitely a standard of care issue. You know, vibration serviceability should have been considered. It was a requirement per applicable codes and standards. And because it wasn't considered, they had a vibration problem that had to be fixed. And that retrofit that had to be installed was certainly not a betterment to the structure. All right, so failure hypothesis. So during the course of an investigation, hypotheses may be proven, abandoned, or revised, you know, based on data that's collected and analyzed. And it's typically at the end of an investigation where a single hypothesis presents itself that leads to the most probable cause or causes of failure. You know, in other words, it is critical that our opinions and conclusions as forensic engineers be well supported. And it's also critical that our reports clearly provide that supporting evidence. You know, in other words, don't do this. All right, so I've got another good case study here. This is a construction defect, and it really showcases testing and data collection to solve a problem. All right, so this is a fairly well-known resort in the Bahamas. You know, you really had to twist my arm hard to be involved in this project. And the resort had recently resurfaced the deck surrounding one of their pools. And And more specifically, they applied what's known as a Thames thin patch material over the existing deck surface to cover imperfections and to re-level the surface. And then on top of that, they applied a cool deck material, which was the exposed surface that was supposed to be aesthetically appealing and was also supposed to keep your feet cool when walking on it. So a little bit of foreshadowing when these overlay materials are installed, surface preparation is critical. So it turns out almost immediately after this new deck surfacing was installed, it started to debond, delaminate, and spall, which is what you see here. And this was widespread throughout. I mean, this pool deck just looked like hot garbage. And to kind of give you an idea of what you're looking at, so the light gray material is the original concrete deck. That darker gray material is that Thames thin patch, which I mentioned was used to cover imperfections and to re-level the surface. And that pink salmon color is that cool deck overlay. So, we were hired by the resort to investigate this issue, to determine why this was happening, and to provide repair recommendations. So I visited the site. I did a very thorough visual evaluation. In addition to that, we also collected some concrete core samples so that we could perform petrographic examination on them. And this is now the second or third time I've mentioned petrographic examination. So what that is with regards to concrete is that it involves looking at that concrete sample under high magnification. And a good concrete petrographer can identify, a number of different characteristics of that concrete sample. They can determine what the aggregate type is, the approximate water to cement ratio. If there's any deleterious reactions going on in that concrete sample, they can see it. If a core is taken through a crack, a good concrete petrographer can also identify the mechanism by which that crack is occurring. In this particular case, we had the concrete petrographer really focus in on that horizontal plane between layers, so that plane between the original deck and the Thames thin patch, as well as the Thames thin patch and the cool deck material. So in addition to doing some petrographic examination, we also did some tension pull-off test, which is the device that you see there in the right-hand image. So this involves gluing a steel puck to the surface and then connecting it to this device that applies a tension force until that puck essentially fails. And this provides us with a couple key pieces of information. It lets us know what the adhesion strength is of these materials. And it also lets us know that when it does fail, where does that failure occur? At what layer? So this slide here shows the different manufacturer installation instructions for both of these materials, the Thames thin patch and the cool deck. I'm not going to read these to you, but I will tell you that based on our on-site observations and the testing that we did, that the contractor that installed these materials violated most of these things. The cool deck overlay was applied too thick. There was a lack of bonding agent between both the Thames and the original deck, as well as the cool deck and the Thames. There was a lack of surface roughening, Existing expansion joints were covered, which is a big no-no. These materials were loaded at very early ages, which again is a no-no. There was elevated water contents in both of these materials, and there was a lack of curing. And we were able to support these conclusions, based on the testing and the test results and the test data. All right, so subrogation. So subrogation refers to the process by which an insurance carrier, and it doesn't have to be an insurance carrier, it could be some other party that's involved, collects money from the party at fault in order to recover funds that have already been paid. And I've got a good case study that kind of highlights this concept. So this is a pretty massive bridge up in the Northeast. This spans the Delaware River between New Jersey and Pennsylvania. And bridges like this undergo a maintenance cycle every few years. And this bridge was recently undergoing one of those maintenance cycles. And the big ticket item for this maintenance cycle was that it was being repainted. And this repainting process is pretty involved. So it involves hanging scaffolding from the bridge. There's a lot of heavy equipment and materials that are used. The existing paint is basically shot with steel shot to remove it. And that steel shot and that old paint has to be collected and prevented from falling onto the ground and into the river. And then it's repainted. Well, it turns out that during these painting operations, on some random day, painters came across this fractured top cord member that you see here. And you can imagine the alarm bells that this set off in the chain reaction that followed. So, because of this, they basically closed traffic to the bridge. They had to install temporary shoring, and they had to perform an emergency repair, which is what you see on the bottom right-hand image. They basically spliced that fractured member. And, this whole thing cost many millions of dollars, not to mention the business interruption that was involved, because this is a tolled bridge. And then, because traffic's no longer going over it, they're unable to collect toll fees. So this is a closer up image of that fractured member. I mean, I'm not lying when I say this thing was completely fractured through. You could literally stick your hand all the way through there. Full disclosure, this was a project that I was involved with my previous employer, and I don't know the final outcome on this, but I will tell you that there was talk of subrogation, and more specifically, the public entity that owned the bridge subrogating against the painters. And the reason why they were going after the painters was because, based on some preliminary analysis that we had done, it had come to light that the painters, it looks like, had overloaded the bridge. As I mentioned before, there was it's a pretty involved process, and there's a lot of heavy equipment and machinery involved. So they were subrogating against the painters to try to recoup and collect money that had been paid out to not only fix the bridge, but also to collect on tolls that they weren't collecting on.
Bradley, 1-minute warning.
Gotcha. This is my last slide. So, to kind of complicate things, this fractured section was removed and metallurgical testing was done. And it turns out that there was a material defect at that fracture plane. So what had happened is that when this bridge was constructed decades ago, this member inadvertently had bolt holes in it at this fractured section. And instead of just leaving the bolt holes as is, somebody had gone in and filled it with weld material. And by doing that, they heated up this section, and it weakened the member at that location where it failed. So, you know, playing devil's advocate, if I were the painters and I was being sued for subrogation, you know, my argument would be, well, okay, yeah, so maybe we did slightly overload this bridge, but, you know, had this material defect not been there, this failure would never have occurred, you know, which we had no way of knowing that it was there in the first place. So a good case study on what subrogation is. And with that, I'll take questions if you have any.
Bradley, we have a question from Tricia Clayton. These are all very interesting case studies. Of all the cases you've investigated, what are the common issues or breakdowns in the engineering process that led to the failures?
So, you know, if it's on the engineering side, it's usually, it involves some sort of design deficiency, either a design deficiency, or if the designer is also part of, you know, involved in the construction phase and making sure that their stuff is installed correctly. You know, I will say that one common theme that I see is that on the design side, just not estimating service loads and design loads properly. And I will tell you, that was a big problem with the FIU pedestrian bridge collapse, is that the demand loads that should have been considered were grossly underestimated. You know, and that's probably, you know, lack of peer review by a supervising engineer is probably partly to blame for that too.
All right. Well, we have another question from Sabika. How did you decide to do failure analysis instead of typical structural design?
You know, I always liked structural engineering. I mean, like I said, when I was in school, my courses were very much focused on structural engineering. But I had a professor that, you know, that kind of convinced me to go to graduate school. And while I was in graduate school, you know, here at UT, I worked at the Pickle Research Center and got to do some pretty cool stuff. And, you know, I think it was there that I even realized that there was this whole forensic world out there. And I just had much more interest in getting into the forensic side of things than the design side of things.
I have a question as well. The FIU case study was fascinating. Did you have to present any of your findings in court?
On that one, no. So the client that we were working for was part of the builder's risk portion of that claim and that failure, and they ended up settling pretty quickly. So I personally and the firm did not have to.
Hello? Looks like we're having some technical difficulties. Bradley froze up for me.
Nope. How about now, guys? Am I back?
I've got you loud and clear.
Okay.
I did have one last question. Have you ever, or any of your colleagues ever, had to present in court?
Yes. Yeah. I've been deposed many times. I've been part of mediation. I've never actually had to present at trial, but I have given other expert testimony, and I've got colleagues that certainly have presented at trial.
Wow. Well, this is about the end of our session. Bradley, thank you so much for sharing your knowledge. Not a whole lot of people know that much about the forensics side of engineering, but it is out there. It's very important. We are told before we take our exams and we take our ethics portion that be prepared as an engineer to defend your arguments, because you'll never know one day when they may have to go to court. And it looks like some of what you're doing, you're the person that's more on the prosecution side, but I guess it could go both ways.
Yeah, it's both for sure.
So thank everybody for attending this session. I think that brings the session to the close, and I'll turn it back over to Lindsay.
Thank you. The recording for this session will now end.